Greetings! Let's take a look at example problem 1 from chapter 5. Using as reference state the hypothetical ideal gas state at 70 Kelvin and 7.83 bars, and with the data given below, calculate the following. Alright, so we have a reference state problem. So the first thing I'm going to do before I even look at A, B, and C is we're told that we're adopting a hypothetical ideal gas state as a reference. So let's go and write our general equation and try and get a handle or make sure we understand what exactly that means. So what I'm going to do is, right, in thermo, we're all about calculating differences in properties. And so I can write the difference between the enthalpy in state 2, right, I'll write as H2 minus H1. In the book, it was just say H and H naught as our reference state. But here I'm just going to have 1, just because, is equal to, and then we're going to write it as a difference in ideal gas values. So H2 ideal gas minus H1 ideal gas plus, and difference in the corresponding residual values, H2 residual minus H1 residual. Okay, so then if I solve for H2, I get the H2 H2 is equal to H1 plus H2 ideal gas minus H1 ideal gas plus H2R minus H1R. Okay. And then from here, what I'm going to do is I'm going to take my difference in ideal gas values, and I'll write that as the integral of Cp dt. So C2, or H2, is equal to H1 plus the integral from 1 to 2 of Cp dt plus H2R minus H1R. Okay, before we plug in the reference state to simplify this, in the table we're given a value for the heat capacity, which is constant. Okay, so I'm going to write this out in one more way. I'm going to write H2 is equal to H1 plus, pull Cp out if it's constant, and I get Cp, T2 minus T1 plus H2R minus H1R. Alright, so now we're told that we're going to use as a reference state the hypothetical ideal gas state at 70 Kelvin and 7.83 bars. Okay. So what that corresponds to, right, if state 1, as I'm using it here, corresponds to my reference state, I'm going to specify the H1 ideal gas is equal to 0. All right, where state 1 is going to correspond to a system at 70 Kelvin and 7.83 bars. Alright, so I'm specifying that my ideal gas value is equal to 0. Okay, so how does that help us out at all? Well, here I have H1 and I have H1R. Okay, so what I'm going to do is I'm going to rearrange. Okay, and I could write this as H2. Okay, is equal to, I'm going to write Cp times T2 minus T1 plus H2R plus, I'm going to group the H1 terms. I have H1 minus H1R. Okay. How does that help us? Well, remember that H1 is equal to ideal gas contribution plus residual contribution. Okay. Therefore, H1 minus H1R is equal to H1 ideal gas, which we're taking or defining as our 0. Okay, so this term then would just be 0 when we adopt this reference state. So what we're left with then in general for this problem is H2 is equal to Cp times T2 minus T1 plus H2R, where state 2 corresponds to my state of interest. Alright, so now let's apply this. Okay. So in problem A, what do we have? Okay. So in problem A, we want the enthalpy of nitrogen at 70 Kelvin and 7.83 bars. Okay. Where we're adopting as our reference date a hypothetical ideal gas at 70 Kelvin and 7.83 bars. Okay. So this is a case where it's interesting because we have that T1 is equal to T2 and P1 is equal to P2. All right, so the temperature and pressure of our reference state are equivalent to our temperature and pressure of our state of interest. So what that means is that our first term, Cp T2 minus T1, goes to 0. Okay, and we're just left with H2 is equal to H2R. Right, and this makes sense because H2 would be H2 residual plus H2 ideal gas, where we're taking that ideal gas value to be equal to 0. Right, and so H2 then would be equal to just this first entry in our table, right? The residual enthalpy at 70 Kelvin at 7.83 bars, which would be negative 5938. So this would be negative 5938 joules per mole. All right, so we've got A. Okay, so that's A. B, the enthalpy of saturated liquid nitrogen at 7.83 bars. Okay, so when I look at the table, okay, at 7.83 bars, Tsat is 100 Kelvin. Okay, so I'm going to take my state of interest, state 2, to be 7.83 Kelvin, or 7.83 bars and 100 Kelvin. Okay, it's going to correspond to this state. Okay, and then, so let me take this one step at a time. So T2 then, all right, my final temperature, so my final pressure was it 7.83 bars? Ah, man, I'm sorry, I forgot already. 7.83 bars and 100 Kelvin. Okay. T1 is going to be equal to 70 Kelvin. And I have that P1 is equal to P2, which is that same 7.83 bars. Okay. So when I look at our general equation, right, H2 is going to be Cp T2 minus T1 plus H2R. Now, in terms of state 2, what's important is we're looking at a saturated liquid. Okay. So if at 7.83 bars, Tsat is at vapor liquid, or Tsat's 100 Kelvin, right? So I have two-phase coexistence at 100 Kelvin at 7.83 bars. So then at 70 Kelvin, I have a liquid, right? And so what I want here is I want the enthalpy of the saturated liquid, right? So I'm going to be dealing with our liquid phase here, and at 70 Kelvin, it just so happens that we have a liquid. Okay, so when I write down my equation, I'm going to have the H2, okay, and I'm just going to make a note that I'm a liquid because we want the enthalpy of the saturated liquid at 100 Kelvin would be equal to, okay, Cp liquid, T2 minus T1. And I'm just making a note. And, we're dealing with, when I talk about Cp here, right, I should be clear, right? This is, Cp of an ideal gas. Right, so let me just clarify, right? This is the term from our ideal gas term. So whether we have, liquid or vapor, right, Cp ideal gas, right, the heat capacity of the corresponding ideal gas state, right, is going to be the same. Right, I'm just putting superscript L on here just to remind myself that I have a liquid phase, right? But now that I do this, I see how I'm going to confuse myself. So I'll keep the ideal gas up there. I'm just trying to remind myself what phase I have. Plus H2R, okay, where again, I'm going to need to make sure I use the corresponding value for the liquid phase. Okay, where knowing the phase is really going to come in is, this residual property where I would really calculate it is using, say, a cubic equation of state. And so if I'm at saturation, I need to make sure I identify which phase is which and pull the appropriate value. All right, so we should be good. So let me just go over to MATLAB just so I can punch it in. Okay, and so CP. So CP is 29 joules per mole Kelvin. Okay. And then we just need, let's write HLR. So this is, or H2 liquid, right? The residual value of my liquid phase, negative 4974. So negative 4974, and that's joules per mole. And then I just need T1 and T2. Okay, right, so I want the liquid value. T2 is 100 Kelvin. And T1 was equal to 70 Kelvin. Okay, so I'd get to H2 was equal to CP, so this is my ideal gas heat capacity, times T2 minus T1 plus H2R. Okay. And so since I'm using SI units, this will be in SI units. So solving to get negative 4104. So H2L negative 4104, and that's going to be in joules per mole. All right, now problem C. Problem C asks for the enthalpy of vaporization of nitrogen at 7.83 bars. Okay. So here, we actually won't even need to worry about the reference state, and we'll go through that in a second. So the enthalpy of vaporization of nitrogen at 7.83 bars. So that's going to correspond to, this row here, 7.83 bars, and we're at our saturation temperature of 100 Kelvin. Okay. So in terms of enthalpy of vaporization, okay, we won't actually need a reference state, okay, because what we're going to find is, delta H of vaporization is going to be equal to the enthalpy of my vapor phase minus the enthalpy of my liquid. Okay. Now, if I were to define, I have a difference in two enthalpies here. So if I were to calculate the enthalpy of my vapor and liquid relative to reference state, and then I take the difference, well, that reference state is just going to cancel out. Right? And so that's where, reference state is completely arbitrary as long as we're consistent, because ultimately we're taking differences in properties, and so as long as we're consistent, that reference state will cancel. So what I'm going to do instead is okay, I can write this as HV minus HL. I could equivalently write that as a difference in ideal gas contributions plus a difference in residual contributions. So I guess I'll call liquid L comma R to be consistent, or V comma R. Okay. Now the key is we encountered first in chapter 3, we showed that internal energy is only a function of temperature for an ideal gas. And then we also showed that enthalpy was only a function of temperature for the case of an ideal gas, right? And so enthalpy is only a function of temperature. So since here I have a difference in enthalpies, ideal gas enthalpies at the same temperature, because at vapor-liquid coexistence, my two phases are at the same temperature and pressure. So difference in ideal gas enthalpy at the same temperature, those are going to be the same, so that difference is equal to 0. So delta H of vaporization, I can just write as the residual contribution to the vapor phase minus the residual contribution of the liquid phase. Okay, and that'll be equal to Well, I already have H2R up here, so let me just make that HL2R. Okay, and then let me get HV2R. The vapor phase would be this negative 401. Okay, so delta H of vaporization is equal to enthalpy of my vapor minus enthalpy of my liquid. All right, and there's no need for a reference state. We're taking a difference, so that reference state would cancel. And then furthermore, the ideal gas term is just zero, because for an ideal gas, enthalpy is only a function of temperature. So since the liquid and vapor are at the same temperature, the enthalpies, the ideal gas contributions to the enthalpy are the same. So we get delta H of vaporizations 4573, and it's positive, just like we would expect. So delta H of vaporization is 4573, and that is joules per mole. And so that's it for this one. I hope it makes sense. Okay. Important part was, working with existing data to compute absolute quantities. But yeah, I hope that helps. If you have any questions, please just let me know.